ancient years. So I organized a workshop in Mainz exactly on this subject. And basically, one person from each one of the experiments. So it's not only the CMB and the supernova, there is Lyman alpha determination, baryon acoustic oscillations. The tendency is the following. Local universe, so supernova, baryon acoustic oscillations, they tend to agree with each other, and CMB tends to disagree. On the other hand, nobody seems to be sure that the discrepancy is really there. And one thing that I didn't know and I learned in this workshop is that there is something bizarre in the Planck data to a certain extent that I didn't know about, is that if you take the low L multiples and you do cosmology only with the bigger scales, and then you take only the higher L multiples, there are some internal discrepancies in Planck too. Okay? But given that, Adam Rees was there, and he doesn't seem to want to admit that there is any sort of unknown systematic in his data. I heard different things from people like Marek Kowalski group working on supernova in Berlin. I'm not a great expert. And frankly speaking, if this is true, it's bizarre. You have to think of outside of the standard model. Frankly speaking, if I just have to extrapolate on what my experience on this thing is that some systematic will pop up. But that's my opinion. It's completely unfounded on whatever you're seeing out there.
So maybe this is a more technical question, but for example, if I, instead of thinking in an S-wave annihilation that we have thought so far, what is the first constraint that comes to one of to your mind if I take a P-wave annihilation? I mean, what's an observable that can I use to constrain P-wave annihilation?
Okay, so no, P-wave, no. So exactly. What he's asking is the following. So far, what I said this morning is that you predict a sigma annihilation. Okay, sigma annihilation is not necessarily constant with the energy. Okay, so far we have assumed that sigma AV. Well, we didn't really assume that. What I said is that if you want to compare this to a benchmark, and you are looking at a benchmark value, the benchmark value is the sigma AV that produces the relic abundance. Is that correct? But this sigma AV is the sigma AV when the temperature of the dark matter particles is something above the GeV, above 100 GeV, okay? Something like that. So if this thing is a function of the temperature, you do expect that in whichever environment the dark matter is, the sigma AV will be different, okay? Now, the simplest thing, so it's called an S wave because only the S wave contributes, and then it's constant with velocity. But if I take it as the constant one is called the S wave, if I take it to be dependent on the temperature, which means on the velocity of the particles, when you have a P wave, that means the sigma A of V is proportional to 1 over the temperature, right? So it's inversely proportional with the velocity, okay? Do you agree with that? So I want a place, otherwise it would be suppressed during the early universe. So I want a place where this is, so I want an environment where sigma A of V is high in order to test it. The CMB bound, no, the CMB bound will be there because you are testing the sigma V at the time of a CMB. It just doesn't mean anything. You do expect everything to be suppressed because the velocity is very small. So if you want to see something, you have to go in a place where the velocity is, no, sorry. Yeah, where the velocity is the opposite. It's the opposite.
V squared, right?
Huh? It's proportional to V squared, or 1 to V squared. Correct. So at the CMB, you can put a bound, but that doesn't mean anything because you expect your benchmark to be very much down. Okay? So you want to go to a place where the velocity is very high. So you, in the dwarf galaxies, you will expect a faint signal because dwarf galaxies are small. So the velocity, typical velocity is 10 kilometers per second. In the galactic center, it's going to be higher. In the clusters, it might be even higher because the mass of the cluster is higher. Okay. There is a paper from Tracy Slater examining, well, she sees it in terms of Sommerfeld enhancement, which goes the other way around. But you can make up your mind from that.
Let's say that you have a model which has a P-wave annihilation, okay? So let's say that this annihilation is super small. I don't care which experiment you're talking about, sigma v is 10 to minus 30, okay? So you won't see with gamma rays, you won't see with cosmic rays, but you can see with neutrinos. You know why? Because the neutrinos from the sun he was mentioning, let's say that you reach the equilibrium. So the rate, the capture rate, and the annihilation rate of dark matter at some point reaches equilibrium inside the sun. So the signal of dark matter annihilation just depends on the scattering rate. That's what he showed, right? So it just depends on the scattering rate. So then I don't care what annihilation is anymore. The only thing we will connect is the scattering rate. If the annihilation rate is really small, I can place a bound on the scattering rate. And you can know what's the scattering rate in your model. You have your model.
Yeah, but they must have gone to
reached
equilibrium.
Yes.
They could have not gone to equilibrium if it's a P-wave.
Depends
so
on
it's
what you got.
complicated.
Yeah.
About that, about this cross section of annihilation, events like clusters collision, like a bullet cluster, it's a good place to search for these things, like to put a constraint on the cross section of annihilation.
No, and the reason is that in clusters there is a lot of dark matter. So let's say that we are now considering an S wave, right? So a constant sigma v. But the point is that your signal from somewhere is depending on the density, okay? And the density and from the background. Now, it's true that in the clusters you don't have gamma rays from the medium, from the intracluster medium, so it's good in terms of background. But the intracluster medium, the density is very small. So the integrated mass of the cluster is very big, but the density is not, it's a shallow density, okay? On the other hand, there's something I didn't completely introduce, we didn't talk about. You might imagine some decaying dark matter models. So you might imagine dark matter models in which it's stable over cosmological times and it starts decaying around now or redshift 1. In principle, it could give you some things. And obviously, the annihilation, in that case, it doesn't depend on the square of the density, it depends on the density. It actually depends on how many dark matter particles you have, because it simply decays, it doesn't fill the others. And in that case, the cluster could be nicer. You can expand upon that, but for annihilation, they're not a good target. People put constraints because it's what it's written in the dedication of the experiments that was done 20 years ago, so they have to do it, but it's not.
About constraints, I don't know if the already been talked, but if you have like a model of dark matter that you can, the particle of dark matter can interact with itself. And what's the constraint? But to this dark matter can't interact via QCD, like strong force, and you have a constraint like that.
Okay, so I will.
We are always talking weekly interacting dark matter.
So let me face the question. Then I will give a first phenomenological answer, and then I will let Farinaldo give you a model-dependent answer. Your question, if I understand correctly, is about what sort of constraints I can put on something that interacts via QCD when I have dark matter interacting with dark matter and doing something and remaining dark matter. Okay? So this is your question. Now, the zero order answer is that whatever I have in terms of this at the leading order, then there are modifications, come from the merging of clusters, okay? Dark matter cannot interact with itself, like, for instance, the gas is interacting with itself, because otherwise it would get stuck. Okay, so I call the interaction dark matter, the self-interaction of dark matter, I call it chi-chi. And these must be smaller than the constraints that I get from the observation of the clusters. Actually, these should be written like this because it depends on, okay? But since it's the same mass, I can take it away. Then, what this means in terms of the interaction, that depends on the Lagrangian, that exactly as it is predicting you sigma annihilation and sigma, it will also predict a self-interaction at dark matter. You can imagine a model like that as long as you stay below this.
I agree. So if you have self-interacting dark matter just like this one, the cross section cannot be that large. If it's this large, you're just going to disrupt whatever galaxy clusters you have. So in order to have a cross section around the QCD scale, if you want, you cannot have 2 by 2. Has been excluded already. So it has to be, you have to change the dynamics. Remember this WIMP miracle I always talk about? It's 2 by 2. So there are models today which are called SIMPs, strongly interacting massive particles, not WIMP. So the only way to survive is instead of if you can have 3 or 4 dark matter particles then producing whatever. The way you do this is because you change how the final abundance you get at the end. The Boltzmann equation for that is much more complicated, but that's the only way you can survive. So if you want QCD scale, this is what you do. So they call the SIMP miracle.
The son of Simp, which is Simpson.
I have some questions for Professor Pedro. From what I read in some papers, the interactions that produce high energy neutrinos, by high energy I mean tera electron volts. They consist of proton-proton interactions and proton-gamma, and followed by pion decay. So I just want to know if there are other possible reactions, specifically in active galactic nuclei that can produce, like leptonic interactions, for instance, or I don't know, some other particles that can decay into neutrinos in those conditions. It's very specific, I know. But
Yeah, well, there's a really easy way to answer is yes. Because active galactic nuclei is a very, very energetic environment, so you have all kinds of processes there, and we know the neutrinos can be produced in several different ways. So yes, any scattering involving any weak forces will produce neutrinos in several different ways. I don't know if this answers your question, or you want some more specific. You have something more specific.
oh,
in
maybe
mind.
it's just that I'm very ignorant in particle physics. So can you give like an example of a leptonic interaction that can result in the production of neutrinos, like some interaction with electrons, accelerated electrons?
Yeah.
You cannot have a product that only have leptons. No, sometimes the people make like a hadronic model or leptonic model for the producer particles. Sorry. Sometimes you have something to call hadronic model or leptonic model to produce, but the leptonic model only can produce photons because it's only have electron and proton, only that. Okay. The only way they could get produce neutrinos, you should have some weak interactions. And these interactions you have, it cannot be only be hadronic. You need to have hadrons in the middle. Cannot be. You only have leptons. You don't have any neutrinos.
Yeah, one example of only leptons producing neutrinos is the muon decay, but you have to produce a muon. So you have to have some hadron involved to produce the muon, and then you have the pure leptonic process.
Okay, and another question would be, okay, how to differentiate between the atmospheric neutrinos produced by high energy cosmic rays and the ones produced at the sources, those sources like an AGN. Like, is like just comparing the energies enough, or?
Well, yes, the energy is the main ingredient, but now we have one other option, which is the direction, right? But the direction, we just started to do this kind of differentiation, looking for where this neutrino is coming from. But apart from that, yes, it's the energy, because it's a muonic neutrino producing a muon close to the detector. So the muonic neutrino is identical if it comes from atmosphere or from astrophysical source. So you have to look for the spectrum, then you use the spectrum to clean up the atmospheric neutrinos, which you already know more or less what is the flux, and then you discriminate the non-atmospheric neutrinos.
Okay, so you have to analyze the whole spectrum to...
Yes, you have to analyze the whole spectrum.
Okay, because there may be some exceptions, right? Like very high energy neutrinos produced in the atmosphere, maybe, by means of very high energy cosmic rays.
Yeah, but it's included in the spectrum. It's supposed to go down very steeply in high energy, the atmospheric neutrinos. So yes, they are there, but they are much less numerous. So if ICTP detect 100 TeV neutrino, it's very safe to assume that is from astrophysical source. But then it's okay, it's 1 plus minus 1. Then when you have 10, it gets better.
Right, thank you.
So I want to add something. So you might also have a dark matter orange to these super heavy high energy neutrinos. So there were some papers. So I've never written a paper on that, but I've seen some papers trying to explain these PeV neutrinos with decaying dark matter. So Orlando wrote one, so you can ask Orlando. Okay, so. Okay.
The ICTP spectrum has some very funny behavior, no? You have a lot of events to low energy and events to high energy, but in the middle you have nothing. But you have a desert. And then you cannot explain this by... And because now then you have people assuming this dark matter decay, try to explain like you have the atmospheric neutrinos, and then the dark matter decay produces these low energy neutrinos, and then you suppress in the middle.
Also concerning this question, I was wondering whether you can correlate information from ICTP about the muonic component of the shower and the neutrino you're actually seeing on IceCube.
If you can correlate, sorry?
The ICTP information. Because you have the muonic component of the candidate shower there, and then maybe you can correlate that with the neutrino information in the cube.
I'm not sure I understood. Yeah, the information is the muonic tracks, right? So these are the neutrinos. Right? Yeah.
No, I'm talking about, I mean, when you have the atmospheric neutrinos, then you have a signal in your cube, right, from his. And then you're asking how you differentiate this from another neutrino coming from the space. And you say, okay, you have direction. Yeah, but you also have ICTP information about their shower.
The remaining shower that produces the... I think it's... Well, maybe I'm lost, but I think it's... I'm wrong, but I think we lost this information much above the IceCube detector. So the only thing from this shower that gets into the detector is the muon neutrino.
I'm talking about the ICTP, exactly. I mean, the muon beta you have. No, I see that. I understand that. My question was whether you can actually get extra information from the isotope as well. But only my question.
So just to comment that Marcel is here, so we are taking questions to Pedro, to Fabio, to Marceli, and to Orlando. And Farnaldo had to leave, so now you're trapped.
If we have the presence of subhalos of dark matter here in our galaxy, how that can affect the models, for example, the Navarro-Frank White?
So again, why don't you ask the organizers to have me giving this seminar? Otherwise, it seems all disconnected. So this goes back again to two questions that was made by one guy that left and by... So you have the rotation curve of the Milky Way, okay? And then you have the one that you expect from the stars, okay? And then people said, well, how this is not really 1 over square of r because it's not a cylinder, because it's not Gauss. Of course, the way you do it is that you take the data of the rotation curve, okay? And the data of the rotation curve are velocities that you observe. Obviously not the dark matter, you observe tracers, gas, stars, there are data. Then you observe the stars, and from the stars, which are distributed in a disk and in a bulge, but they're not really a disk and a bulge. There is a density of stars, which is a function of r, theta, and phi. Okay? From that, you solve it exactly with their green function. You compute the potential in the entire sphere. You take the potential in the plane of the galaxy where the stuff is there, and then you compute the tangential velocity. My student Maria has decided to be in Spain, otherwise she would be telling you that because her entire thesis is on that. And at this point, you look at what you expect from the stars in this very range. Okay? So you have, if you want, you have a V observed as a function of the radius, and then you have a V predicted as a function of the radius, baryonic, okay, whatever is in the star. Now, these two, that's why I asked you to perform the exercise about V square, these two things are a function of the radius there. So you can fit the missing component at each point. Of course, you have to have a density profile, right? You are fitting, you're not really fitting in the space of the velocities, you're fitting in the space of the density, which will give you a velocity. And you have to make an assumption for what the shape of this is, the density profile. So you typically say, I like it to be spherical for good reasons. I like it to be a power of the radius with a constant, okay? So you fit the slope and you fit the constant. And that gives you a result. That result, if it's -2, it's the perfect NFW, which we know it's not the answer to the problem because it's taken from n body only. But that NFW is that r to the -2 that I invited you to compute yourself. What happens in the center is more complicated because the baryons interact, the error bars are big, the dark matter contributes little as you expected because there is from stars. So if you fix this index to be 1, well, -2, but it's formulated in a different way, you are fitting a Navarro-Frank White and you're just fitting the normalization. You're really fitting exactly a little bit the shape. This is a broken power law in reality. It's compatible. Navarro-Frank White is compatible with the halo of the Milky Way, but the answer is a little more complex than that.
My question is to Marceli. There are any prospects? I already heard about this, but from we have the gravitational waves to study the early universe, like beyond the SMB?
So, so I think the question was about prospects of using primordial gravitational waves to study the universe at earlier stages than we can reach SMB. Yeah, that is part of the, say, it's another aspect, right? So we are not talking anymore about astrophysical sources of gravitational waves, but as fluctuations, tensor perturbations in the early universe generating gravitational waves. That is very exciting as well, but I think that it is in a much longer time scale, you know, in terms of detectors that could be capable of seeing that because it's very, very small signal. So what we hope to see before that is an imprint of those tensor fluctuations on the cosmic microwave background, provided that we can control the foreground sources of systematics. So I would say that for now, I think it's I don't think that it's a realistic prospect in the near future.
Still regarding to the AGN question, I would like to know in which region does the neutrino production taking place? Is it only in the jet?
The neutrino production inside the ice cube, where they are the AGNs. Oh, well, it's we are still establishing which kind of mechanism, the neutrino production mechanisms. So, but again, it's a very rich environment, so it can be produced in several different ways, right? So these ones we are looking, probably it's coming from I don't know, the production of these hadronic showers, pions and proton and neutrons interacting, and from these jets also you produce neutrinos. I would bet that it's something related to these hadronic interactions, and not those two others that I presented, the radioactive decays producing only electroneutrinos. It's not that. For sure it's not that. It's something more related to hadronic interactions. One thing that I didn't say, one calculation that IceCube presented, which is very interesting. It's of course not produced only in the jet, so they can estimate what the total amount of neutrino, high energy neutrinos, this kind of object is producing, and it's higher than the photon total energy. So they are saying that okay, the energy coming from neutrino is arriving here, and part of the energy coming from the photon are lost in interaction with the environment between the blazer and here. But of course, there are some heavy production on the jet, but it has also some spherical, symmetrical components.
If I may use this privileged space to, seems that you are interested in blazars and high energy phenomena right now. So we're trying, at the moment it is scheduled, we still have to see if it will really take place, but next summer, exactly winter, in August, we should have a 2-week school on high energy astrophysics here, okay? And one person that has been contacted is Kota Murase, who's a great expert in gamma ray bursts and neutrino production in blazars. If he agrees to, if the school takes place and he agrees to come, that you might learn some more. The other advertisement is about the Dark Matter South American Workshop. It's the 2nd edition. It will take place here in November. Not a school, so it's going to be slightly more focused, but there are posters. It's going to be November.
My question is for you. It's a basic question that always puzzles me. So you talk about the modulation, the physics behind the modulation. So it's a difference of velocity between us here in Earth and the dark matter. But something that I never understood, it's when you form the galaxy, well, we conserve the angular momentum and it's spiraling. So the dark matter interacting only gravitationally will not spin with us, rotate along with the galaxy.
This is an excellent question. This is really an excellent question. So what's going on? And it's related to the formation of the galaxy. So this is not a rigorous answer as most of the things I told you, but you have the potential well, okay? Say that you can imagine an instant zero in which dark matter and gas are just sitting there and there is a density distribution. They're not flat, because for stability, but they're not peaked. Sort of, they're the same, they're parallel. And they are virialized. That means basically means that there are, let me see if I find another color. There are gas particles all over, virialized, okay? And there are dark matter particles. They are virialized, it basically means that they reach an equilibrium with the gravitational potential. They have the same f of v, and their motion is entirely random, okay? So they're just moving around. Good? Now, what happens to the gas? The gas is collisional and radiative. So once in a while, some gas can hit itself, like it, and deheat itself and cool down, right? Because it radiates away. So it can lose energy, but it cannot lose angular momentum. Therefore, what it does, it sits in a disk. And this disk is rotating. The dark matter that was distributed all over cannot lose energy, cannot lose angular momentum. So it just keeps going. So in this huge mass, this huge perfect gas of particles, the disk will be rotating. Okay? And will have a peculiar velocity.
So this is why we have a disk and a sphere.
This is also the reason why we have a disk of stars
and a disk of sphere of dark matter.
It doesn't happen in all the galaxies, but mostly, yes.
Okay, so now let's take a last question so that we can go earlier to the break for the clips. Okay, so this question sessions have been great. Unfortunately, we will not have them next week because time is very limited. But you know, Fabio is not only organizer, but is professor here, so he will be available to discussions, as he said several times during the week. Eduardo Ponton, which will give the next seminar, is also from IFT, so you can also contact him. And of course, I know everyone will be available to get questions by email and so on. So this is not the last lecture of the day, but it's the last moment that we see in the lectures, Orlando, Marcelli, Pedro, and Fabio. So I would like to thank them for the participation this week. Okay, 15 minutes coffee break, and then Eduardo Ponton with accelerators, and then Eclipse.